Hi guys, Mrs. Valdivia here, and today we're going to talk about Chapter 10, Interactions of Particles. So this is our interactions of our solid, liquid, and gas, and as we talk about this, we're also going to move into our gas laws and whatnot. All right, so we have three different states of matter. These states of matter are solid, liquid, and gases, and there's interactions that happen between all of these particles. So a solid, particles are close together and they're held in place. So when we see a solid, we see that all the atoms are nicely organized, compacted together. This allows a solid to have a definite shape and a definite volume. A liquid, particles are close together but move freely past each other, right? So because of that, as you can see here, the particles are still close together, but they're moving freely from each other, right? Giving it that fluid-like motion. They get a definite volume, but the shape adapts to the container. So that means it doesn't have a definite shape. So if you take a bottle of water and you throw it into a bowl, right, you still have your 8 ounces of water, but it's not in the shape of that long container, right? It's in that bottle. It's now in the shape of that bowl, the bottom part of the bowl. A gas, the particles are far apart from each other, and the particles have minimal interactions with each other. They don't want to be close to each other. They're floating around doing their own thing. This gives them no definite shape and no definite volume. And the gas will adapt to the shape of the container. So it's going to adapt to the shape of the container, or the volume, actually, not shape. So let me write volume, to the volume of the container. So if you have a container, 22.4 liters, right? Your gas will go in and try to fill those 22.4 liters of that container. All right. Now, a phase change is a transition from one state of matter to another. So a transition from one state of matter to another. And we can transition from a solid, a liquid, and a gas. Okay. And the way we transition is we can go from a solid to a liquid to a gas, then a gas back to a liquid, and a liquid back to a solid in the reverse form. We can also get some sublimation and go from solid to gas, or vice versa. Okay. So those are our phase changes that something is able to go through. And our phase changes, the amount of energy required to go through a phase change, all varies depending on the type of bond that you're actually going to have. Here we have an ice cream, and you can see that an ice cream easily melts, right? It starts melting. And we know that strong forces between particles create higher melting and boiling points. So if this is taking a while to melt, then it might have a strong force. If it's melting really fast, then it's going to have a weak force between the particles. Let's actually talk a little bit more about these forces and the types of energies that are inside of these forces. So I wrote down kinetic energy and potential energy. And kinetic energy is energy of motion. So energy of motion. So just a little recap from our chapter 8, I believe. And potential energy is stored energy. Okay, so not in motion, right? And right here, I wrote down KE for kinetic and PE for potential energy. And we want to see a solid. Does it have high or low kinetic and potential energy? Well, because it's a solid, it's not really moving. So it's going to have low kinetic energy. And because it's a solid and it's not moving but has the potential to melt, break, release energy and everything, it's going to have a high potential energy. So here the kinetic energy is low and the potential energy is high. Now if I look at a liquid, the liquid's kinetic energy is average, but so I would say the kinetic energy and potential energy. So I'm going to still say kinetic energy is on the lower state, low to medium state. And the potential energy is a bit high, but it's less or lower than your solid. Less than a solid. Now let's go into a gas. A gas has very high kinetic energy and very low potential energy. Okay. High kinetic energy, low potential energy. So going from that, let's look a little bit more about the structures that we see. So we know that ionic substances make lattices, and lattices are basically just a framework of atoms that are grouped together, right? So as you can see here, this is a lattice, the top lattice. So like a lattice on top of a pie, right? It's nicely grouped together in a line. That's the same thing here. So they're grouped together and aligned in a very rigid-like structure. Let's look at these metallic substances. Okay, so electrons tend to move throughout all our particles, from solids, liquids, and gases, right? And all our particles have different types of bonds associated with them. So let's talk about the movement of our electrons. So movement of electrons. And our metallic substances. So I'm going to just title this metallic substances. And the movement of electrons in a metallic substance is very fluid. Even though a metallic substance is a solid, the electrons move freely throughout it. Okay? And all our metallic substances form lattices that are tightly packed together. So the movement of electrons is very fluid, and they form lattices of tightly packed atoms. Okay. So an example would be, so if like all of these right here, like what we see in the image, if it was copper, the copper atoms are very tightly grouped and knit together. And it doesn't have to just be copper, it could be any kind of movements. And inside of this lattice, you're going to have your electrons freely moving between them. So if I make this a little bit bigger, you can see that even though it's packed together, there is little spaces in between the copper atoms. And in between these copper atoms, you're going to have your electrons that are freely swimming through them, moving around as they will in their own free little space. Okay. So they're moving tightly, but they're still moving around the metal atom. And this is partly due because metals are positively charged. So the electrons are just being shared between them. The electrons are actually, what they say is circling the atom itself, but because it's circling, it could easily jump from one atom to another and vice versa to stabilize itself. So they kind of just free flow of electrons. So electrons swim freely. I'm going to just say that. Electrons swim freely between the atoms. And you're going to say, well, why is that even important to know, right? Well, have you ever wondered why people are attracted to a metal object? Let's see if we can see this here. All right. So as I move this here on this little metal object, we have some shiny, right? And it'd be probably shinier if I polished it. Well, that shiny that we see as it's moving through, it's actually your free flow electrons that provide the shininess that we get to see. Okay. Now, the shapes of electrons can be easily altered. So, shapes of metal are easily altered. Okay. And the way that we alter the shapes is through different forms, right? Like a penny, when you put a penny inside a machine, right, and you crank the machine, and all of a sudden you get an image, and the penny is stretched out, a nice little oval shape instead of a round shape, but it has an image in it, right? So you can stretch, and you could basically pound an image into a metal object, right? The same way that people made swords back then. Like if you look at blacksmiths, right? They were pounding the metal, heating it up, turning into different shapes than things that we see in our everyday life and use. But we don't think about that this metal object, we use it because it's easily shaped, easily maneuvered. And the words that we use for this is malleable and ductile. So let me see if I find. Yep, here we go. So it is ductile. And ductile means stretched. It can be stretched. And it is malleable. Let me make sure I spell this right. Malleable. Which means you could hammer it down. Hammer down. Apply pressure to it and it won't break. So you could apply pressure without it breaking. You could stretch it without it ripping. All right. Now, this part right here, I'm going to have a little explanation that I'm going to put for it for our electron movements. Metallic atoms hold the outer electrons. Okay. And this is due to the lower nuclear charge. And if we recall, the nuclear charge is just a charge of attraction between the positive nucleus and the electrons. So remember, cations have a lower nuclear charge. They tend to be, well, cations are positively charged, and metals are cations, right, when they form ions. Okay, so metallic substances, like we said, can easily be bent and molded. If you look at this blacksmith, same thing. They molded your metal. So remember, gold, lead, we could easily make different things from them. Now let's look at the forces inside of them. So the forces within the molecules and forces between the molecules. There is different forces, and we want to make sure that we can identify what these different forces are. Okay. And actually, I'm going to put a little separation here, because now that we're going to speak about the forces within the molecules, this is going to apply to all of our molecules. So not just the metals that we were just talking about. So this is going to apply to all our solids, our liquids, our gases. Okay. So we have forces within molecules. And we have forces between molecules. All right, so the forces within the molecules are going to be our covalent forces, and the forces between the molecules are going to be our intermolecular forces. Okay, so forces within, I said, are going to be covalent. And the forces between the molecules are going to be our intermolecular forces. I'm going to write that down here. So what does that mean? Let's go ahead and take a picture. Take a look at this image, right? We have two different types of forces. So in this first part right here, let's just look at this one molecule, right? The single bonds and the triple bonds. The single bonds and the triple bonds right there are your covalent bonds. Those are your covalent bonds. And if we recall, covalent bonds means the sharing of electrons. Okay. So the covalent forces are going to be due to the sharing of electrons within your molecules. So sharing of electrons within the molecule. All right, let's go with a quick example of that one. Let's use a different color. So using the same example that we can see here, hydrocyanide, right? Yummy. No, just kidding. That is a joke. Hydrocyanide is not yummy. All right. So we have HCN, right? The covalent bonds are going to be right here. These are our covalent forces. Now, if we look at the forces between molecules, this is the forces that hold the different molecules together. One way that I like to explain this is people, right? We are held together by covalent forces, yet when we hold someone's hand, we make a bond, and that bond is an intermolecular force. So on this one, we're now going to draw a couple of these. And another right there. And okay. So now I have three molecules, and these three molecules, I am going to just close them up so that we can easily see that they're molecules. Okay. And these molecules are going to be connected together through intermolecular forces. let's use a different color. That's not a good color. Okay, so intermolecular forces holding these together. All right, like I said, again, it's like a person. So I'm going to draw a little stick figure here. Okay. And this person is being held together by covalent bonds. So covalent bond holds this one person together. And this is just an example, little like analogy. It's not, we're made of more than just covalent bonds. So covalent bond holds person together. Now, if I have another, yes, people are going to have very long arms. Okay. Okay. So in my stick figure people, now they're holding hands, right? And maybe, who knows, we're making like a chain of people, like little kids playing or something. Right? All of these are intermolecular forces. So it's an intermolecular forces. So the intermolecular force holds people together. I wish I could spell on a regular day. Together. I guess that's why I'm a chemistry teacher, not an English teacher. Okay, so intermolecular force holds our people together. So just so we can now start understanding that there is a difference between both of these. Okay. What do the intermolecular forces tell us? The intermolecular forces tell us how strong or weak the bonds are. Because not all the time do people hold hands together in like this, tight bond, right? Sometimes they're like holding it like this or like this, or kind of just like C-clamped attached, right? Little pinky hold, whatnot, fingers touching, I don't know, right? So sometimes the bond isn't as strong, and we know that, right? When we're playing Ring Around the Rosie or something like that, like there was always one group that the hands got let go. It wasn't that strong. So intermolecular forces let us know how strong or weak the bonds are. All right, so now let's go ahead and talk about our networks. So we have different kinds of networks that form with our bonds, right? Our covalent networks, so remember, those are within the molecules. Let's take a look at this diamond, right? And this piece of graphite. They're both made out of carbon, but you'll notice that the shapes are different. In this diamond, when the atoms combine together due to high heat and high pressures, right, they form a tetrahedral shape. So you see here's the center point, and it has 1, 2, 3, 4 sterics attached to it, right? That's a tetrahedral shape. And this tetrahedral shape has proven to be one of the strongest shapes that a molecule can actually form. Now, same thing. We have carbon in its other form. This is carbon in graphite form. And we notice it doesn't have a tetrahedral-like shape. If we look at a center atom right here, we see 1, 2, 3 connections to it, right? So look at another one and you're going to see 1, 2, 3. So this is a trigonal planar kind of shape. So it has a trigonal planar. And the trigonal planar is what allows this one to be more brittle, soft, and something we use to write with as opposed to something we create lasers with. same thing, but different. So this is how we can see also in our covalent compound that they're not always similar. So we're going to call these our covalent networks. Okay. And they're the lattices of covalent bonds that form giant molecules. And like I said, both of these lattices can be slightly different. So in a covalent bond, one thing that we want to know is that it's not metallic. And because it's not metallic, electrons are not free moving. Okay? They're not free moving. So they were free moving in our metals, but they're not free moving in our covalent structures. So the electrons are not free moving. And if we remember, our covalent networks are between non-metals. This is because it's the sharing of electrons between non-metals. So just a quick little reminder on that one. I know we hear it every chapter now and now, covalent versus ionic, but just in case. All right, so the example that we had a carbon tetrahedral-like shape. I'm actually just going to draw the connection here. So here we had that connection, and then I'm making even though they're all carbons, I'm just trying to emphasize the shapes by making the central atom darker. Okay. So you could see that a diamond forms a tetrahedral shape, right? So this is our diamond. And the shape that it's forming is tetrahedral. And it builds up on each other, right? So it's going to build up. And it's super strong. Now, the other one that we had, so this is all carbons, remember that it's just carbons, is our graphite. And our graphite shape was a trigonal planar kind of shape. And this trigonal planar shape actually makes it kind of brittle, right? It's not as strong as our very tetrahedral shape. So this one gives it a trigonal planar. When you thought your shapes weren't going to be around anymore, you're like, what? All right, so we got a trigonal planar shape, and it's more of a flat-like design, so they're flatly layered on each other. So this one is building up, right? Like a tower. It builds up like a nice, strong, sturdy tower. While this one right here is like flat layered. So it's a flat layer on top of each other. And this makes it brittle because of that flat layer. It's kind of like pieces of paper on top of each other, so it's a flat layer. All right. Polymers. So polymers are slightly different. Polymers are made out of different materials, and these contain long chains of covalently bonded atoms together. So plastics is one of our most common polymer, right? So they're just, one more time, polymers are long chains of covalently bonded atoms placed together, right? Um, Plastics are rubbers. Here I see a potato, so I'm gonna assume probably a potato has some polymer, but I don't know about that, so don't quote me on the potato, right? But as you can see, it's just a long chain of covalently bonded atoms. Okay. So in summary, ionic substances um, form lattices. Metallic substances are tightly packed together with free moving electrons. Molecular substances, which is our covalent networks, have covalent bonds and intermolecular forces. Covalent networks form different types of giant molecules, while the polymers form long chains. So diamonds, right? Nice little big structure. Polymers, a long chain that's similar to our plastic. Okay. So now we're going to talk more about our forces. And we're going to go from our covalent forces and start talking about our intermolecular forces. So continuing with this one, we are now going to talk about the intermolecular forces, which are the forces between the atoms. So the strength of intermolecular forces, well, that's going to vary depending on the atom that you actually have. Okay, so depending on the structure is what I meant, and the connection between those structures that are formed. We have three common types of structures or forces that are made between these molecules. So we have dipole-dipole interactions, hydrogen bonds, and dispersion forces. So depending on the type of force that you get, it's going to result in different types of physical properties that are going to form. The first one that we're going to talk about is going to be the dipole-dipole interaction. So this is the dipole-dipole. Now, the dipole-dipole interaction is going to be an attraction between covalent molecules. Okay? And what we mean about that is the attraction between non-metals and non-metals. So we're going to write these things down and then show our examples. So it's the attraction between our non-metals, which are polar covalent molecules. Now, not all non-metals make polar covalent. Remember, sometimes they're just covalent, in which covalent means that the electrons are being shared equally. Polar covalent means that the electrons are being shared, but it's not an equal kind of sharing. So in this example, we have hydrochloric acid combined together. And in hydrochloric acid, we know that chlorine has all the electrons around it. It has 7 valence electrons. So there's 7 valence electrons around it. And chlorine is also more electronegative based on the electronegativity chart, and that it's farthest to the right, closer to fluorine. Fluorine having the highest electronegativity of 4.0. So with that being said, we don't even have to look at the chart. We already know that all the electrons are going to be around chlorine, giving it a negative dipole. And that means that hydrogen will have a positive dipole. When we show a dipole moment, A dipole moment is basically showing the travel of the electrons. How do they travel? Well, the electrons travel this way, which means they're going to be concentrated on this area. And again, what does that tell us? That tells us that we have an asymmetrical sharing of electrons, right? So most of the electrons are going to be in this part of the cloud. Okay, so they're going to be hanging out on this part of the cloud, and very few of the times will they be where the hydrogen is at. So this is an asymmetrical pattern. That asymmetrical pattern lets us know that this molecule is a polar molecule. Now, how do these molecules connect, and how do they even attract to each other? Well, if I have two polar molecules looking like this, right, where the electrons are concentrated on this area, the electrons are concentrated on this area, what's going to happen is that the negative chlorine, the electrons from this negative chlorine, are going to attract to the positive hydrogen. Remember, we still have a dipole here. We still have a positive dipole and a negative dipole on that end. So these dipoles will attract and connect. Okay, so they're going to be sticking together, as one might say. So if a molecule has a net dipole, the molecules of the compound tend to stick together. So if molecule has a net dipole, the molecules of the compound tend to stick. Kind of like glue, right? So they're stick together. Or magnets is the best example that we can have this. Same side magnets repel, while opposite sides of the magnets attract together. And this is going to be due to the attraction of a positive dipole and a negative dipole. So of the positive dipole and the negative dipole ends. So these are the ends right here. This is this end and this is this end right here. So remember, like I said, this is like an asymmetrical kind of point of view. You're gonna see these also in this kind of format. Let's see if I could actually draw this. Where we're gonna have, and you're gonna see shading in this section, like two different types of shading to represent that they're two different like little parts where the electrons are on one side more than they are on the other side. Okay. So in this flask, what we see here is two flasks. You'll notice that in one flask you have more molecules, and in the other flask you're going to have less molecules. It's less condensed. So in the first flask, the one that has more of them, these molecules are attracted to each other, and they're attracted to each other because of the dipole, which causes them to get closer together, right? That means that they're going to have a higher melting point and a higher boiling point. So let's make sure that we add that to our notes. Okay? So these dipole interactions are going to have a, so compared to no net dipole. That means that there is no dipole movement like this one, so no net dipole. These polar covalent compounds are going to have a higher melting point, MP, and a higher boiling point, BP. And that's due to the attraction of the high amounts of energy required to pull them apart. So it's due to attraction between them, between the molecules, and the high amounts of energy required to pull them apart. All right, so let's just look at this dipole-dipole interaction so we can look at the geometry. In this case, carbon dioxide has a linear geometry. And even though oxygens have a negative dipole, it's going to be symmetrical, right? So it's going to have a symmetrical like shape, which is going to mean that the electrons still spread out evenly throughout. Therefore, although it has a positive and negative dipole, it's not going to have a dipole moment. Okay, so it's not going to have one of these dipole moments. This one's going to be shared equally, which means that its dipole moment is going to be 0. And it's going to have a low boiling point. Okay, now let's go ahead and look at the next one. Okay, sulfur dioxide has a dipole moment. So both of the oxygens have a negative dipole, and sulfur is going to have a positive dipole. So that means that the electrons are actually traveling downwards because this is a bent-like structure. It's bent. So because of that, it's going to have a small dipole associated with it. This next molecule, acetonitrile, I finally pronounce it. Okay. If you notice, the carbons have the positive and the nitrogen has the negative dipole. Therefore, there is a dipole moment occurring here. And it's a large dipole moment. So therefore, the boiling point is going to be much higher. It's going to take more energy to boil acetonitrile than it will to boil sulfur dioxide or carbon dioxide. So as you can see, the bigger your dipole moment, the higher your boiling point is going to be. That means it's going to take more energy. High boiling point, high amounts of energy. Now, hydrogen bonding has a similarity to it. So if we look at this one, okay, we have methane, hydrogen cyanide, and water. And this is going to be based off the mass. Okay, the mass, how much it weighs, right? So the dipole moment for methane, which weighs, I would say a minimal amount, has a dipole strength of 0. The mass for hydrogen cyanide is 27 units or AMUs, and a dipole strength of almost 3. The water is a bent-like structure and has 18 AMUs, atomic mass units, and it has a dipole strength of 1.85, so it's like medium, right? So if we look at the boiling points, okay, you're noticing that the boiling point of this one is very low. However, the boiling point of water, even though it has less mass than hydrogen cyanide, is a lot higher. Why is that? Why doesn't it follow the same rules as when we did a dipole-dipole interaction? There is a big difference. So in dipole-dipole interactions, you'll notice that you don't see hydrogens, right, connected in these dipoles. So we see the hydrogens connected in the carbon, but not in this particular dipole right here. Okay? We're talking about hydrogen bonds, right? And these ones are now connecting to their hydrogen bonds. Water has a specific hydrogen bond. In order to make a hydrogen bond, you have to actually be bonded with hydrogen, oxygen, nitrogen, and fluorine. So it has to be those elements in bonded, right? So hydrogen has to be bonded to oxygen, to nitrogen, or to fluorine. And it actually spells out the word hump. So we're going to actually write those down in a little bit. So a hydrogen bond has a higher boiling point than a dipole-dipole interaction. So it requires more energy. Okay, let's go ahead and look at hydrogen bonds now. Put it on a different paper. So we're looking at a hydrogen bond. It's going to be a strong intermolecular force. Between molecules containing hump. HONF. Hump. Hydrogen, oxygen, nitrogen, or fluorine. Okay, so you have to have, in order to have a hydrogen bond, you have to have a connection that looks like one of these. So that's 1, 2, 3, 4, 5. Like that. All right. So actually ignore the electrons. I don't even know why I spent my time doing that, because these are going to, they are bond with something else or they create ions. Okay, so it only occurs with these is what I want to say. It's only going to occur with your hump, right? So let's take another look at what our hydrogen bonds look like. Okay, so in the hydrogen bonds, like here an example, you see the nucleus of hydrogen is just one proton, while the nucleus of fluorine involves a whole bunch of protons and some neutrons inside of them, right? And fluorine is extremely electronegative. It's the most electronegative element that we have. So here we have a connection in which these hydrogens are attaching to the bigger masses of fluorine, making it multiple hydrogen bonds. So let's go ahead and draw these out. We have hydrogen right here, and we're going to have fluorine over here, right? Fluorine is highly electronegative. Okay, so now we're going to have a couple more of these. And it's always good to draw out your examples as opposed to just looking at them, because it helps you actually remember. Remember, metacognition is our muscle memory, and our memory will actually remember the things that we write down. So that's why they say copy something. Copy it so many times and you're actually going to remember it. And that is going to actually allow you to learn something. Okay, so you can create a hydrogen bond with fluorine, and you could create another hydrogen bond with that same fluorine. Remember, these are temporary bonds, but these temporary bonds are extremely strong and they will last a long time. It's going to take a lot of energy to break apart these very strong hydrogen bonds. So fluorine is electronegative with a negative dipole, and hydrogen has a positive dipole. The dipole moment moves like this. This is a very polar molecule. Now, if we look at the different forces that we have, right here you're going to have your intermolecular force, and in this one is going to be your covalent bond force, right? And our intermolecular force is a hydrogen bond. That's the one that we're looking at. And we're going to actually draw those on here. We're going to label them. So the bond between this hydrogen and that fluorine is a covalent bond. They're unequally sharing electrons. Covalent bond. And you know what? Let's just go ahead and write that. Unequal sharing of electrons. Which actually means it's polar covalent bond. So it's a polar covalent bond. And this right here, this connection is our intermolecular force. And the type of intermolecular force that it is a hydrogen bond. So remember, these hydrogen bonds, this area here, right? That area radiates positive energy. Radiates positive energy. So it means it has like a positive charge associated to it. And that is due to the exposed nucleus. Due to hydrogens. If we go back and look at this image here, right? You remember I said hydrogen just has the one proton. So the normal hydrogen that we see on the periodic table has a mass of 1 and an atomic number of 1 because it has 0 neutrons. Therefore, it has a very exposed nucleus, as opposed to fluorine has protons and neutrons protecting its nucleus, its core center. So this right here is just bursting positivity. And that's creating a strong attraction. Okay? So this radiation or radiating of positive energy attracts the more electronegative elements. So it attracts the more electronegative elements, which we said are oxygen, nitrogen, and fluorine atoms. This means that the atom will get very close, actually exceptionally close, to hydrogen's nucleus. Hydrogen's nucleus, creating a super strong covalent bond. All right. So if you want to think of a hydrogen bond and something helps you remember the hydrogen bond, literally I would draw like muscles or something, right? Like here's a hand and muscles. Okay, I can't really draw muscles. And here's the hand. All right. Muscles. A muscle hand, right? It's flexing because it's strong. The next force that we have is quite the opposite of our covalent bonds, right? They're not that strong. And it's going to be a London dispersion force. This image, good image. So talking about hydrogen bonds, surface area. Hydrogen bonds is what allows strong surface area in water. That's why little bugs, you have the water crawlers and water walker things, like they could easily move through it because of that high surface area or surface tension. And the reason you have that is because of the hydrogen bonds creating these strong bonds and layers between each other. The other example is water collecting on top of like the water collecting on top of a bottle. I'm gonna actually look up an image, see if I could find one and show you guys what a nice hydrogen bond actually looks like in a kind of like a real world example. We've seen them in, you can actually do a penny experiment where you open up where you put some drops on top of a penny and you could see that the the penny collects the drops. Here's a penny image. Okay, so if you look at this image right here, it's our little penny image. Open a new tab. Okay, that might actually take too long. Okay, that's taking too long. All right, but you can see that the water is in drop-like forms on top of that penny, right? So same thing here. Okay, it's in drop-like forms on top of that penny, and that's due to that strong hydrogen bond, that strong intermolecular force that allows that to happen. Okay. Water bottles also get that little thing of water on top of it, right? Due to that strong hydrogen bond. All right. So now, like I said, we're going to talk about a different force and not exactly the strong force. This is going to be the opposite of force. This is going to be a London dispersion force, okay? So London dispersion force is going to be a weak intermolecular force that's going to result from instantaneous dipoles that happen. So these instantaneous dipoles are just like on and off, constantly on and off. So they're pretty weak. I say a joke, and it's just like a joke to help us remember, is the song London Bridges Falling Down, right? Well, not to say that their actual bridges were weak, but, the bridges got bombed down, right? And all the bridges broke. And then they got rebuilt in London, and some of them broke again, and same process going through it. Okay. And we're not getting into the history of them, but London dispersion forces, I'm like, oh, London bridges falling down, falling down. So this is the same thing. London dispersion forces falling down, falling down. So they fall down, they come back together. They fall down, they come back together. So click off, click on, that kind of thing. So our third one is the London dispersion force. London dispersion force. Sometimes you'll just see it as a dispersion force, but like I said, it's going to be the weakest intermolecular force. So it's the weakest intermolecular force. Okay. And it results from instantaneous dipoles. Instantaneous dipoles. Okay, so if we look at this image, what we have is the instantaneous dipole connecting these bonds together. So very, very weak form of attraction that creates with them. Okay. So they form and break away easily. They forms and breaks apart, then reforms, easily and instantly. So like I said, London dispersion force is not real much of a force there to look, well, I'm not going to say to look at, because it's actually a force that holds things together. And so an example here is like our hydrocarbon chains. So we know that our hydrocarbon chains are non-polar. So what does that tell us? London dispersion forces are the only force found in our non-polar molecules. So it's the only force found in non-polar molecules. So these are like molecules with long hydrocarbon chains. So an example would be long hydrocarbons. Okay. Now the hydrocarbons is just carbons connected together with hydrogens around them. And you could have a double bond hydrogen. You could even have a triple bond, between the carbons, not hydrogens. So that'd be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. You know what? Let's just give that a double bond. So I could say 4, and then that's going to be. All right. So that's an example of a hydrocarbon. Okay, an example. And in this example, right, that we have right here, we're going to connect it to another hydrocarbon. So we're going to have another hydrocarbon. And it doesn't even have to be the same hydrocarbon. It could be a different hydrocarbon. Okay. So let's say we're connecting it to this hydrocarbon. Okay. And what we're going to have is between these are going to be instantaneous dipoles that form, but they form and break apart right away. They do not stay connected together. Okay. So what causes this weak instantaneous dipole is that there's going to be a weak dipole between these molecules. So an example would be like, and this one, like, I'm just using it as an example, not true to the molecule itself, basically because I'm not going to do the formal charges of them. But let's just say that this carbon here picked up a slightly positive, and this one here picked up a slightly, or this one over here, a slightly negative charge, right? And throughout the whole thing, and then the same thing here. Maybe this one picked up a slightly negative and it's slightly negative. So these slightly little tiny miniature dipoles, they're so weak, they don't really exist. They just keep like a blink of an eye kind of thing. You know, you don't think about them, but they're there. Okay. All right. So let's go through a quick little summary of our forces here. The hydrogen bond is the strongest of them all of the intermolecular forces. That's like when you're holding your hands and you're holding hands, right? You're like, super tight grip, you know, or that kind of grip. You're like, I don't know. You have the dipole forces. So these are the molecules that have that net dipole, that have that asymmetrical sharing, right? So that's also a nice grip, like a firm handshake between them, right? But it's like one of those handshakes that last a while. And then you have the London dispersion forces where you're like, I don't know, you know, kind of like you're walking past people and they keep rubbing on your shoulder, but you make a slight connection as they walk past you. So it's a very weak bond. Okay. All right. The next section that we're going to go through is we're going to start actually describing our gases. So now that we're described our intermolecular forces, we're going to describe our gas laws and the way that gases move and react with each other. So in describing our gases, gases are everywhere around us. They're in our atmosphere and everything that we see. So in the sky itself, the sky is composed of many different gases. You have argon, oxygen, nitrogen, hydrogen. You have carbon dioxide, carbon monoxide. Water is even in there. So all of these are different gases that exist in our own atmosphere. And we want to know, well, how do gases even behave? Well, one, gases are as far apart from each other as they can possibly be. They have a very high kinetic energy. So real gases and ideal gases, no matter what, they have high kinetic energy, which means they're in constant motion. Constant motion. Okay. And they're going to have as little to no interaction with each other as possible. Now, gases can be described in two ways. It can be described as real gas or an ideal gas. So a real gas is basically like our everyday gas that we have. Gases are far away from each other. They're spaced out. And when they collide, and they bounce off of each other, right? So take a bouncy ball, throw it on the floor, and it goes, right? Pretending that the floor is just another ball, right? That you're bouncing it with. Or billiards, you play billiards, and the two balls hit each other, and then they spread apart and they move. So that's a real gas. What that means is that when a gas molecule interacts with another gas molecule, there's actually a reaction. Something actually happens. So there's friction, it bounces away, it changes the direction of that gas. In ideal gas, it's a little bit different. So ideal gas, we're saying that the particles do not interact at all. So the volume of the particle is going to be less than that of the container because they're going to spread about and bounce on the container walls. Okay, and they have zero interaction with each other. So it's kind of like they're going to go, just slightly move away from each other and keep walking. They're going to mysteriously miss each other every single time that there's an interaction. So that's an ideal gas. Let's go ahead and write some of those down. So an ideal gas, it has much less volume than the container. So and that's because the molecules are spread apart due to the molecules being spread apart. All right, and there's zero interaction with each other. Zero interaction between the particles. Now I'm using the word particles because it could either be atoms or molecules interacting with each other here. I really don't know because it's just a general term for this one. Okay? So if we look at ideal gas is going to have a standardized temperature, volume, and pressure. So it's going to have standardized temperature, volume, and pressure. So ideal gas, let's write that down. Standardized volume, pressure, and temperature. Okay. So all of these are going to be standardized, right? And we have different values for each one of them and different ways of finding them. So the first one we're going to do is pressure, right? So pressure is the force that is exerted on their surroundings. So basically, if I have this hand and my hand represents a gas and the gas goes and collides with my other hand, there's a force. We could even hear that force, right? How much force is force per unit area? Okay. So our pressure is equal to force per unit area. So area, force per area. Okay. And that is the gas's pressure that it exerts on its surroundings. And if it's inside a container, it's the force that it's exerting on the walls of the container. So if we think about a container being completely empty, it will actually implode, right? So that means it squishes itself in and goes, right? As opposed to exploding. So yeah, look at my cheeks. If you look at my cheeks, this is an explosion. And an implosion is going to be like sucked in. So that container, a gas container, when it's completely void of anything, including all gases, it will implode because there is no force on that area, right? So you need to have some sort of gas, even if it's just air inside of it, in order to keep it as is. Okay. So it's force per unit area. When measuring pressure, we have different units that involve in the measurement of pressure, right? So there is gravitational pressure, there is atmospheric pressure, tire pressure, even the pressure of like moving around or bouncing a ball. So the force exerted on all these different types of pressures. Okay. So when we measure pressure, we use a barometer to measure the pressure. Okay. And like I said, pressure is the force exerted on the surroundings. Exerted on surroundings. Okay, and we use a barometer to measure atmospheric pressure. Right. So actually, I'm going to write that over here on a new little line. I don't want to try to squish things together in here. So pressure in the atmosphere can be measured using a barometer. So that's how the weather stations actually take the pressure, right? Have an atmospheric barometer. So an atmospheric barometer is in the old school kind of ways, you would take mercury. So they had a tube. It was quite simple. They had a glass tube and another container with no lid. And they basically filled the glass tube with that had little increments on it with mercury. And as the pressure changed, the mercury would fall or rise up, knowing what would be the pressure. So a higher pressure, atmospheric pressure, that means the atmosphere is very heavy, it's exerting a lot of pressure on us, would cause the mercury to go up. A lower pressure would cause the mercury to go down. And that's actually how they would look at the weather system when they were going to have a hurricane or a tornado or a different kind of event that's going to happen weather-wise. You could tell using this simple barometer. So like I said, the barometer was measured in millimeters of mercury. So it's barometer. It uses millimeters of mercury. So that stands for millimeters of mercury. How many millimeters did it actually go up? And I skipped an L. Boom. Millimeters of mercury. Okay. Now, 1 millimeter of mercury, so this is our unit, so our equalities are starting to come up. 1 millimeter of mercury is equal to 1 torr. Okay. And torr is another unit that we actually see for atmospheric pressure. So therefore, the average pressure at sea level, okay, at sea level, so at sea level, the average is going to be 760 millimeters of mercury. So this is the average pressure. Or you could say 764 average. Okay, so at sea level. And because of that, knowing that this is at our sea level, this right here is going to be considered our standardized pressure. Because at sea level, at 1 atmosphere of pressure, we have the equivalent to 760 millimeters and whatnot. So this right here, this is going to be our standard pressure. And I'm going to rewrite this so that we could see it. 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr. So these are interchangeable. That means that we can create conversion factors from any of these equalities. So if you have to convert 1 atm, you could say over 760 torr, or vice versa, right? You could reverse them. You could say 760 millimeters of mercury in 1 atmosphere, right? It goes on and on and on. Okay, there's different ways you can use this to make conversions for your math that's going to come up. Okay. So measuring pressure, like I said, it's basically the air pressure pushes down. As the air pressure pushes down, right, your vacuum is going to go up. A gauge basically tells us what our pressure is going to be. So when we have compressed gas, like gas inside of our tires, we can use a gauge to tell us that difference in the pressure, right? So the pressure of the gas versus the pressure of the atmosphere. Now, the PSI unit we don't use as often. However, that's not to say you might not see it on your test. So let's go ahead and make sure that we include these units of conversions in our notes. So this is our units of conversion. So this is conversion unit. Okay. And we had this with these conversions as examples. So these are equalities. But we also have the following. 1 atm is equal to 14.70 psi, pounds per square inch. So that's how we measure the tires. Or it's also equal to 101.3 kilopascals. And actually, kilopascals you will see a lot. You will see this conversion, atmospheres to kilopascals, throughout. If you want to finish writing this out so it could all be just one beautiful thing, you could include your millimeters of mercury and include your torr on here. And these are going to be all your equalities that you can use to turn into conversions. Oh, and I forgot the 1.01 bar. That's how little we've used a bar. 1.013. I've totally forgot about it. Okay, so now remember, now we've just talked about ideal gases. We talked about the standardized pressures and the units that we use to convert the standardized pressures. This is going to lead us to different laws, right? And these laws are what we use to calculate and figure out pressures, temperatures, and all that. And it's going to lead to the combined gas law as well. So the first law that we're going to look at is going to be Boyle's law. Right. Now, the pressure of a gas in Boyle's law states that as the pressure of the gas increases, so Boyle's law states, oh my God, just repeated myself. Pressure increases, volume decreases, and vice versa. Okay, so as the pressure increases, volume decreases. And that's assuming that you're going to have a constant mass and a constant temperature. So what I drew here are two different containers to try to explain this. So this is going to be my container number 1, or my initial container. And this is container number 2, or my final container. And you'll notice that I wrote this law down. This is Boyle's law right here, using those two analogies. So whichever one you want to use to help you remember, pressure 1, pressure 2, or pressure initial, pressure final, whichever one. Right. Now in here, I'm going to have a liquid. So my liquid is floating, or sorry, a gas, not a liquid, a gas. Okay. And a little piston. And in this first one, I'm going to be pulling up on my piston. So here's my piston. Okay. And as I pull up on the piston, so we're pulling up, that means I'm going to release the pressure. Okay. And to release pressure means to decrease the pressure. And if I'm decreasing the pressure, what's happening to the volume of my gas? Is my gas compressing or is my gas expanding? As I release the pressure, the gas expands. Therefore, the volume increases. On my next container, I'm going to be pushing down on the piston. So we're going to be pushing down on the piston. And as I push down on the piston, so it has a downward motion here, and this one had upward motion, my molecules are becoming more compressed inside of this container. Okay? They're more compressed inside of the container. So pressure increased. So we had an increase of pressure, and that caused for compression. That led to compression of the gas. Which then in turn led to the gas, the volume of the gas decreasing. So the volume went down because of that, because our gas compressed. So as pressure increased, gas compressed. So Boyle's law, again, not super difficult. It deals with pressure and with volumes. Let's go ahead and look at this problem. A commercial compressor stores 2.8 liters of air at a pressure of 150 psi. If this air is allowed to expand until the pressure is equal to 15 psi, what volume will the air occupy? Okay. So in this example problem, okay, I'm going to look for my initial or my pressure 1 and pressure 2. The compressor stores 2.8 liters of air. So volume initial is equal to 2.8 liters. The pressure is 150 psi. It says if this air is allowed to expand, so it's opening up, and we know that if it's expanding, we're going to have less pressure and we're going to have more volume. So we're expecting to have more volume. So it expands until the pressure is equal to 15 psi, just over atmospheric pressure. What volume will the air occupy? So volume 2 or volume final is unknown. We don't know it. But pressure 2 is now 15 psi, much less pressure. So we're going to go ahead and solve this problem and calculate. So using our equation here, we're going to just fill it in. So pressure 1, 150 psi, times volume 1, which is 2.8 liters, is equal to pressure 2, 15 psi, times volume 1, which we have, so volume 2, which we don't know what it is. Have no idea what that is. So we're going to solve for this, and the way we're going to do it, quite simple, just a little bit of algebra. We are going to divide both sides by 15 psi. Now that we've divided both sides by 15 psi, that cancels out because it just goes to 1. PSI unit and the PSI unit also cancel out. It goes to 1. We're left with the unit of liters, which is the unit of volume, and that's what we're looking for. So if I rewrite this now, I'm left with 150 times 2.8 divided by 15. And this is all in liters. Actually, I'm not going to put that unit. I don't want to confuse you. Equal to volume. Right? We get a handy dandy calculator, and whoop, I pushed something. Too much. Nope. we went way ahead of this one. All right, here we go. So we're going to put this on our handy dandy calculator and see what we get. Okay. And in this case, we got 150 times 2.8 divided by 15, and I get 28. And let's see if we're correct. Boom, 28 liters. So volume is equal to 28 liters. We want to make sure that we have the correct number of significant figures. If I look at the original problem, I have 2, 2, and 2. So my answer should be in 2, and it is in 2. So volume is equal to 28 liters. You notice that here they manipulated the equation before writing the numbers in. That is actually perfect. That's actually my preferred method of doing that. So basically, I'm going to rewrite it here just to show you that equation manipulation. P1 V1 is equal to P2 V2. I want to solve for pressure. That's what I want to solve for. Or sorry, volume, not pressure. I want to solve for volume. I need to isolate volume, so I'm going to divide both sides by P2, canceling that out, and therefore P1 V1 over P2 is equal to V2. And that to me is a lot easier to do this first and then put the numbers in, because sometimes you can mess up in writing your numbers and forget a digit or a decimal of some sort. So we're going to go on to Charles' law now. Charles' law deals with volume and with temperatures. It does not deal with pressure. So this is that constant pressure. What happens to volume and temperature? Well, as your temperature increases, your volume also increases. And vice versa, if your temperature decreases, your volume will also decrease. Okay. The equation for this one is V1 T1 is equal V1 over T1 is equal to V2 over T2. Okay, so one thing to note is that our gas expands when it gets hot. Okay, so that's what I was going to write right here, is that gas expands when heated. Okay, so the warmer it is, the more the gas expands. So you could look at their tires in the winter versus tires in the summer. In the winter, you always have to add air to your tires. You end up getting lower air pressure. And in the summer, you get higher air pressure. Why is that? Well, because in the summer, your gas molecules are moving a lot faster and they're creating a lot of pressure inside of your tires, right? They're expanding to fill that actual volume of the tire. In the winter, your gas molecules are moving very slowly. They're really cold, so they're slowing down. So they're not expanding as they should to fill up the volume of that tire, thus creating a lower temperature, a lower tire pressure. Okay. So using Charles' law, I also want to use another thing, like, let's look at a balloon instead of just tires. So a balloon. If I have a balloon, right, I'm going to have two balloons, a summer balloon and a winter balloon. So this is my summer balloon, and this is going to be my winter balloon. Okay. Now, in the winter, it gets cold. So even though it's the same size balloon, in the winter, it's cold, right? Okay. There's not much of temperature on that one. So it's a cold weather. Right here are all my things. Chin, 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 chin. So it's cold weather equals smaller balloon. And if we explain that, that's because, just like in the tires, the molecules are not moving. Molecules they're moving slower, and not filling the balloon up. So it's going to take more air to actually fill it up. While in the summer, right? Okay, the thermometer is really hot. So in this one, the balloon fills, so it's hot weather, which equals a bigger balloon. Bigger balloon. And the explanation for this one is that the molecules are moving faster. Just going to take up this space. Molecules are moving faster and fill up the space. So they're not as sluggish. They're moving a lot faster. That means they have higher kinetic energy. So there's that kinetic energy again. Kinetic energy is really high in the summer for our gas, and kinetic energy is lower in the winter for our gas. Right? In this picture, you can see the same thing in our temperatures versus our volume of our different gases. And yes, Charles' law was used to find absolute zero. Absolute zero, which was given to us by Kelvin, was actually studied before by someone else. I don't remember who it was, but Kelvin is the one that actually put it on the map per se. Right. So if you look at our gas, right, the volume increases for all our gases, no matter which gas we had. The volume increases as the temperature got warmer. Okay, so as the temperature got warmer, the volume increased. Even in this one, it was a slight increase, but it still increased. All right. So in the Kelvin scale, remember we had standardized pressures and standardized temperatures and whatnot. Okay. So our standardized temperature is going to be our 273.15 degrees Celsius. Trying to see if I find my, here it is. So with that, we can actually write that down on our temperature for our standardization. That's 273.15 degrees Celsius. And that is equal, actually negative, is equal to 0 Kelvin. Okay. And one of the conversions that we do with this one is that Kelvin is equal to degrees Celsius plus 273.15. So this is actually the equation to convert Kelvin into Celsius, right? And most of the time, like this one says, they work to the nearest degree. I would make sure to write the 0.15 down, not just write the 273, because you get better accuracy in your problems. All right, so let's go ahead and solve a problem using Charles' law. A balloon has a volume of 3.2 liters at room temperature, which is 25 degrees Celsius. The gas inside the balloon is heated to 100 degrees Celsius. What is the new volume of the balloon? Okay. So here's an example problem. Volume 1 is equal to 3.2 liters. Temperature 1 is equal to room temperature, which is 25 degrees Celsius. Volume 2 is unknown. Temperature 2 is equal to 100 degrees Celsius. Okay. We want to find out what is volume 2. So we're going to write our equation down. And we are solving for volume 2. So quite simply, we are going to isolate volume 2 by multiplying both sides by T2. This allows T2 to cancel out. And now I can rewrite this as T2 times V1 over T1 is equal to V2. I'm going to go ahead and start putting in my information. So I have 100 degrees Celsius times volume 1 of 3.2 liters divided by temperature 1 of 25 degrees Celsius. Now that I have those, I can cancel out the units of Celsius, and I am left with liters, which is what I am looking for. So volume, the answer is going to be in liters. Okay. I'm going to go ahead and put this in my trusty dandy calculator. And I get 12.8 liters. Now, if we take a look at our significant figures, ooh, well, what happened here? Here, we transformed it into Kelvin. Lesson. All right. And I completely forgot about this. So this is a good example and a learning moment for us all. When we're working with gases, there was a reason why I showed you that equation earlier. When we're working with gases, we always have to convert our Celsius into Kelvin unless stated otherwise. Always convert Celsius to Kelvin. Degrees Celsius into Kelvin when working with gases, okay? When working with your gases. And then if it says, oh, what is it in Celsius? You're going to have to reconvert it again into Celsius, okay? So this equation right here is not going to work for us, okay? Is not going to work because the unit for temperature for a gas is going to be Kelvin. So let's go ahead and redo this really quick. All right, in order to convert this into Kelvin, remember Kelvin is equal to degrees Celsius plus 273.15. Okay, that's the equation we're using. So we have 25 plus 273.15, which gives me 298.15 Kelvin. I'm going to do the same thing here, and that's going to be 373.15 Kelvin. Basically, I'm adding 100 to it. All right. So these are going to be our new numbers that we're going to actually use. So volume 1 is 3.2 liters times temperature 2, which is 373.15 Kelvin, divided by temperature 1, which we got 298.15 Kelvin. Now our units of Kelvin can cancel out, and we get to solve our problem. And I know it shows an answer on here, but like I've said before, it's always a good idea to solve your problems on your own, not just rely on a PowerPoint, because a PowerPoint can actually have typos. In this case, it doesn't. The answer that I got was this ginormous 4.00496. I'm going to write it all out, and then we will write it in correct number of significant figures. And it's in liters. Okay, so if I look at the original problem, I have two significant figures here, two significant figures here, and here I only have one significant figure. It didn't give me two significant figures. So my actual answer, I'm going to write down in one significant figure as opposed to two. 4 liters. All right. Now, the best law of them all is the law that we don't actually have to, the one law actually that I say you remember the most, because with this law you could solve anything, right? Now that's not to say you shouldn't know what Charles and Boyle's law are, but if there is one law when it comes to solving all math problems relating to real gases, it's going to be the combined gas law. So let's go ahead and talk about the combined gas law. So the combined gas law is basically putting together Charles Boyle's law and Guy-Lussac's law. Guy-Lussac's law, we didn't talk about it really here because we don't use it much. You use it more in physics. I believe if you take any physics classes, let me know. But so this is just going to be the combined gas law, putting everything together, right? Um, the reason why we use the combined gas law is because in real life, you're not going to really have a unit that's going to be constant, which means not changing. Like in an air conditioning system, right? In the air conditioning system, it responds to the changes in temperature and the changes of pressure outside, right? And the volume of the gas is going to expand or increase as well. So the combined gas law is just putting it together. And the best way to do this is not to actually just solve a problem. It says a gas with a temperature of 280 Kelvin, a pressure of 200 kPa or kilopascals, and a volume of 25.8 liters is compressed to 15.8 liters, causing the pressure to increase to 350 kilopascals. What is the temperature of the gas under the new conditions? Let's do this. All right, so write everything down first. So pressure 1 is 200 kilopascals. Volume 1 is 25.8 liters. And temperature 1 is 280 Kelvin. Wonderful. It gave it to us in Kelvin, so we do not have to convert from Celsius to Kelvin. All right. Now let's look at 2's. Okay. So pressure 2 is 350 kilopascal. So that means the pressure increased in this. And the volume was compressed to 15.8 liters. It wants to know what the new temperature is. So we have no idea what that new temperature is. So we're going to go ahead and solve this problem. I'm going to rewrite it. P1 V1 over T1 is equal to P2 V2 over T2. I am going to be solving for T2. Okay. And the way I'm going to solve for T2, I'm going to multiply both sides by T2. That allows that to go away. And now I'm going to just rewrite this as T2 times P1 times V1 over T1 equal to P2 V2. Now, why did I do that? Why didn't I just move P2 V2? Well, because T2 is at the bottom, right? And I don't want it to be at the bottom. I want it to be on the top. So I have to try to isolate it. So I'm not done yet. Now that I have T2 on the top, right, I need to go ahead and move these ones to the other side. So I'm going to do what I did previously. I'm going to use a different color here. I'm going to multiply both sides by T1. Okay, so that allows T1 to cancel out. And I'm going to divide both sides by P1. So actually, I'll do that different steps for you guys. So T2 times P1 times V1 is equal to P2 V2 T1. Okay. Now I'm going to go ahead and divide by P1 V1 on both sides. These units go away, right? It all goes to 1. And I am left with T2 is equal to P2 V2 T1 over P1 V1. You don't have to do it in all of those steps. I obviously showed every single step just so you guys could stay with me, and in case there's someone who's having a little bit of difficulty with this. If not, if you know how to do that, you're right, that you're going to bring this here, all of this went to the bottom, right? All of this to the bottom and this one to the top. That's it. All right, let's go ahead and plug in and solve. So therefore, T2 is equal to 350 kilopascals times V2, which is 15.8 liters, times T1, which is 280 Kelvin, divided by P1, which is 200 kilopascals, and divided by V1, which is 25.8 liters. Okay, now that I have that, I'm going to go ahead and cancel out those units that repeat on the top and the bottom. Kilopascals cancel out. Liters cancel out. I'm left with the unit of Kelvin, which is the temperature, and that's what I want. So I'm going to go ahead and solve my problem. Now, if you want to rewrite this without the units, you can. So I'm going to just do that to show you guys and help you if you need that extra visual. I have that, and I'm going to go ahead and solve for my missing variable. So 350 times 15.8 times 280. Oops, wrote the wrong thing. Times 280 equals that. I'm going to take that and divide it by 200. And I'm going to take that and divide it by 25.8. Okay. And my temperature 2 is equal to 300.0775 Kelvin. Right. And now we're going to fix it and put it in the correct number of significant figures. If I look, here I have 2, 1, 3, 2, 3. So I'm going to prefer to put this in one significant figure, okay, which is going to basically be rounded to 300 Kelvin. Okay. Remember, these zeros are not significant because there is no decimal. They're just trailing zeros. Right? And that was the combined gas law. And the reason why I said the combined gas law is like if you remember that on a test or anything where you don't have open notes, you could solve the rest of your problems, because if something is constant, like if volume was constant, you would ignore, just cross it off. If pressure was constant, you would cross that off. If temperature was constant, you'd cross it off. So whatever's constant, you just take it off of the equation and solve for the rest. Okay. So that was for our combined gas law. All right, so all our gases, we have all these different laws, right? And it leads to something else. It's going to lead to our ideal gas law, right? So the combined gas law and the ideal gas law. So we know we have the mole, and the mole is used in everything. It's used in our gases as well. So Avogadro's number, right? 6.23 times 10 to the 23rd. Oh my goodness, I hope I said that right. Avogadro's number is the number of particles in 1 mole, right? The molar mass is the amount of grams in 1 mole. Ideal gas also deals with the mole, which is how many we have. So Avogadro's law is if the temperature and pressure are constant, the volume of a gas is proportional to the number of moles of gas present. What that means is that the number of moles that we have are going to affect the volume of our gas. So in Avogadro's law, we're stating that if the pressure and temperature are constant, then the volume of the gas is proportional to the number of the moles that are present. So what that means that at equal volumes of any gas, it's going to contain the same number of particles or molecules, right? And this is at STP. So STP stands for standard temperature and pressure, which is the ones that we went over earlier on the video. And our standard temperature is 273 Kelvin or 0.15 Kelvin. 0 degrees Celsius, but don't use Celsius for our gas, which we learned why. Gives us a wrong answer. And our standard pressure, which is 1 atmosphere. Okay, so at STP, right, we're going to get the following. 1 mole of any gas occupies 22.4 liters. So at STP, the volume of any gas is 22.4 liters per mole in 1 mole. So in 1 mole. So if you have 1 mole of gas, you have 22.4 liters. Of what gas? I don't care. Doesn't matter what gas you have. 1 mole of gas, there is 22.4 liters. All right, so let's look at the ideal gas law now that we have some understanding of what all these little things are and how they come together. Ideal gas law is PV equals nRT. So where P is our pressure, V is the volume, that's not going to change. N is moles, T is temperature, and who knows what R is? Just kidding. R is going to be a constant. It's a specific number depending on your pressure. So it's a constant number that changes depending on the unit of pressure. Now, if we keep everything as we should, like we keep it in atmospheres and in Kelvin, then that R value should equal 0.0821 liters times atmosphere per mole Kelvin. Right? So this is what this R value would actually be if we keep everything in consistent units, right? Kelvins, atmospheres, and liters. So the units must match. There is different R values. You could easily look up your R values for an ideal gas. Okay? All right. Well, the best way to solve and learn anything is just by solving them. There's not much to say about this. That it's just a problem we got to solve. So let's go ahead and take a look at this problem and figure it out. What volume does 1 mole of gas occupy at a temperature of 0 degrees Celsius and a pressure of 1 atmosphere? So let's go ahead and write all our things down. Volume. What volume is unknown? It's X. It's a question mark. Does 1 mole, so N is equal to 1.00 moles, of a gas occupy at a temperature of 0.00 degrees Celsius. That is equal to 273.15 Kelvin. And a pressure of 1.00 atmospheres. Perfect. It gave us super easy numbers to work with. So let's do this. PV is equal to nRT. We are solving for V. We're solving for volume. So therefore, I am going to divide both sides by pressure. That allows pressure to cancel out. Now I have volume is equal to nRT over P. So I'm going to solve it. I'm going to use this space down here. Volume is equal to 1.00 moles times my R constant, which is right over here, 0.0821 liter atmosphere per mole Kelvin, times my temperature of 273.15 Kelvin, all divided by my pressure of 1 atmosphere. Okay. Now I'm going to go ahead and cancel out all of these units so we don't get confused. So atmosphere cancels out with atmosphere, Kelvin cancels out with Kelvin, mole cancels out with mole, and I am left with liters, and that's exactly what I want in order to solve for my volume. I'm going to go ahead and put everything in my trusty dandy calculator. So that's going to be 0.0821. Okay. This is just a 1, so I'm not going to even bother. Times 273.15 equal to that, divided by 1. I'm not going to divide it by 1 because it's just 1. So my answer is equal to 22.425 something liters. And like always, we want to put everything in significant figures, and everything is given to me in 3 significant figures, which is going to be right there. So my actual answer is going to be 22.4 22.4 liters. Now, does that make sense to us that it came out to 22.4 liters at STP? Remember, we had STP because what is STP? STP is, where do we go? I wrote it down somewhere. 273.15 Kelvin. Look at that. 273.15 Kelvin was our temperature. Pressure is 1 atmosphere. Oh, would you look at that? We had the pressure of 1 atmosphere. 1 mole. We got 1 mole. And when we solved the problem, what did it give us? It gave us the 22.4 liters. I don't care what gas it was. Doesn't matter what gas you have. You're going to get 22.4 liters in 1 mole of any